Okay, hello everyone. Let's start today's session. I hope you all had a great day so far. Today we are going to talk about the Thevenin theory, Norton theory, superposition, and a little bit about the power consumption. And we are going to get ready for this week's lab assignment, which, as I probably assume that you see in the canvas, I made an announcement because this week on Thursday, if I'm not mistaken, there is going to be the career fair. So, which I strongly encourage you to attend that career fair. It's going to help you a lot, even if you are not looking for like immediate kind of like a job interview or connecting to the specific industry. It's a good opportunity to get a clear perspective about these kind of stuff because before you know it, the college is going to be over and you are going to graduate and you need to actually start working in industry. So I encourage you to attend that because I wanted to like give you the opportunity, as I mentioned in a canvas in an announcement, we will extend this week's lab assignment for one extra week. So it's not due this Sunday, it's due next Sunday. So if you want to like attend the career fair and you are gonna lose any lab session on Thursday, it wouldn't affect your performance on the lab assignment, and you could continue that on the next week. Any question regarding the previous week or general aspects of the course? No? Go ahead. No, we are going to push back everything, like, because that would be a little bit more challenging to do both of them at the same week. Yes.
So we still go to the lab this week and
Yes, you have this week and next week to do that too, which is quite a lot of time. This is not like a very kind of like complicated task, but to be fair for people that have the lab session on Thursday and they want to like attend that, I extended a week so everyone have the kind of like the same opportunity to finish this lab assignment. Anything else? We're good? Okay, next, let's start with our lecture if it works for me. Okay. First of all, let's talk about start our discussion with why actually we care about those theories, the Norton, Thevenin, and superposition theory. And why bother to talk about them, why bother to learn them, and why we need to like actually experience how to apply them in the lab. Okay? This theorem is basically the tool that help you to simplify when you have to simplify your analysis when you have a complex network in hand. It could be like a network of resistors or more complicated system. You might have like multiple sources in your system. As you move forward towards your studies and courses, you are going to end up with way more complex system that you need to analyze. So Thevenin theory and Norton theory and superposition would basically help you to simplify those complex circuits and easily be able to like solve for the variables and the parameters that you want to focus on and it's important for you. Now, let's start with the Thevenin theory. I am going to go a little bit fast because my assumption is that you already know about this theory from the circuit one. Okay, so I'm just gonna do that as a reminder and then move on to the lab sections. Now, the key idea of the Thevenin theory and also the Norton theory, is that we want to deal with the complex circuit or whatever system that we have as a black box. Okay, so you always have a certain desired parameter that you want to analyze. It could be a voltage, it could be like a load that you have. You want to see what's going to happen to your load when you kind of like analyze and simulate your system, or there is a power that you want to find out. All that kind of like situations can be simplified using a Thevenin theorem or Norton theorem. How? When you take that variable or the component that you might focus on out like individually and deal with the rest of the system as a black box. Okay, so we don't care what's in that black box is. All we care is what's going to happen in the terminal that our desired component is attached to that black box. Is that clear? So now there are two ways that in a circuit theory, okay, that we can represent any type of system, any the behavior characteristics of two terminals, regardless of what is attached. Okay. One is using the Ohm law, okay, which says, okay, the voltage and the current observed from each terminal is going to be related to a certain impedance or resistance. And use the Ohm. All right. So what we can replace that black box with is if we know the voltage across those two terminals, and we know how much current we can drain or inject between these two terminals, then we basically know what's the most important. Basically, we know everything about that black box. What's happening inside it doesn't matter because it doesn't affect us. What affects us is what's happened on those two terminals. Now, Thevenin theory is going to simplify that black box using a series connection of a voltage source and a resistor. Why voltage source and a resistor? Because as we said, on those two terminals, what we need is the voltage and the current. Okay, so the voltage source would provide us, or what would simulate, basically, represent the voltage that is going to be applied to that terminal by that complex circuit. And that resistor would determine or estimate the current that we need to analyze or to represent that black. Is that clear what I'm saying? So in order to have a voltage and current, so we can represent the whole system as one component, one black box, okay, we need a voltage source and a resistor. That way we can have voltage across the terminal and current injected to that terminal. Are we good? Now, to calculate what value of the voltage source, you need to create the alternative circuit that we call it a Thevenin circuit. In order to calculate that, you need to eliminate the component outside of the black box. So those two terminals are going to be open circuit, okay, and let the rest of the circuits run in normal condition. Whatever voltage that you get on the terminal is going to be the Thevenin voltage that you are going to use in your alternative circuit, in your Thevenin circuit. Now we said we need also a resistance. In order to estimate the resistance that you are gonna see from that terminal that is important for us, so we are gonna, come on. Watch our system from that terminal, and we want to see what type of impedance or in DC resistance we see. Okay, how to estimate that? We are gonna, first of all, the terminal is still open circuit. Okay, next step is to deactivate all the sources. How to deactivate? All the voltage sources are going to be short circuited. So you replace all the voltage sources in your circuit with a short circuit, and you are going to replace all the current sources with an open circuit. When you take out those sources and replace them with a short circuit and open circuit, now you have just like a network of resistance that you know how to simplify. If they are in parallel, you know how to calculate them, and if they are series, you know how to estimate the equivalent resistance of those connections. So you know how to calculate the total resistance that is equivalent of the whole network. That resistance is going to be your Thevenin resistance. Are we good? So this is basically the very simple explanation of the Thevenin theory and how to basically calculate the voltage of the Thevenin and the resistance of the Thevenin. Now, if you attach the components that you wanted to analyze to this Thevenin circuit, what's happening to that component is exactly the same as if you analyze the whole original circuit and you watched that desired component. Make sense? Now, the concept of the Norton theory is exactly like the Thevenin, just one little difference. Before, we used a voltage source, the Thevenin voltage, and a resistor in order to estimate the voltage across that terminal, that output terminal of ours, okay, and the current that is going to be either drained or injected from that terminal. Okay, now in order, instead of voltage source, we use a current source and a resistor. We are still using Ohm law, so we are going to connect a current source in parallel with a resistance, so we know the current injected either to or out of, in or out of that black box. Okay, and using that resistor and the Ohm law, we know how much voltage is going to be across that term. Same concept is just instead of the series connection of the voltage source and resistance, we have parallel connection of current source and resistor. Now, when you want to calculate or estimate the Norton resistor, is going to be the same as before. So it should be clear that if the a process of calculating the Thevenin resistance and a Norton resistance is exactly the same, and our circuit, for example, is not changing, so we can basically get to the conclusion that the both resistance should be equal to each other because the circuit is not changed. And in order to calculate that, we short circuit the voltage sources inside our circuit and open circuit the current sources. So both networks are going to be the same. Therefore, both Norton resistance and Thevenin resistance that you estimated for a specific circuit should be the same. And it is. So whatever you calculate for Thevenin resistance, if you want to calculate the Norton resistance, it's going to be the same value. Okay? Now, any question? No? Okay. Now, when you want to calculate the current injected, the current of the Norton resistance, Norton circuit, that current source, what you have to do is you eliminate that a component that is connected between the two terminals, that desired component, and you replace it with a short circuit. Okay, so what that means? That means the Norton current is the short circuit current between the two terminals. So you short circuit the terminal and you calculate the current that is injected through that short circuit. Is that clear? Are we good on that? Okay. Now, any question about Thevenin and Norton? No? What is superposition? Because, as we mentioned before, the systems that we are dealing with, at least in this level of the kind of like electrical engineering, we can consider them as linear. Okay? That means if we have multiple sources in our system and we have a desired output to kind of like analyze, because the system is linear, that means we can analyze that desired output one source at a time. Okay? So when you have two sources, for example, in this circuit, you can deactivate one and run the analysis. Let's say you want the current I3. Okay? You deactivate one, run the analysis, then you do the same for the other one. So you deactivate the other one and run the analysis on the first deactivated source. So each source at a time, and you find the same parameter that you want. In this example, that I3. Now, because of the linearity in the system, the ultimate result, the total I3 is going to be the summation of the two calculations. So if you did the circuit B, analyze the circuit B, and you have I3 prime, and analyze the circuit C, and you calculated the I3 double prime, okay, your I3 is going to be the summation of the I3 prime and I3 double prime. This is the characteristic of a linear system. And it doesn't matter how many sources you have. It doesn't matter how complicated the circuit is. It's always. Is that clear? Now, remember, the general assumption, the base assumption is that our system is linear. Okay? In this level of the electrical engineering, you are normally dealing with the linear system. But when you move forward and you want to like work with a nonlinear component, then you need to be careful using the superposition, because then your system is not linear. Are we good? Now, any question? Let's go through the lab assignment that we have for this. On the first assignment, we wanted to like just go over various simple ohm laws, okay, and try to estimate the voltage across resistor in our networks. Okay. Now, when you want to solve such a problem in theoretical solution, you have two options in how to solve or analyze this series. the hard one and the easy one. The hard one is to go direct. So you have a two-loop network, for example, network A. You run a two-loop KVL and solve these two equations, okay, and find out all the voltages. Okay, that's in this system, because it's just a two-loop and like three resistor, is not gonna show how complicated this approach is compared to the next approach. But when you have more complex network, then you're gonna see how devastating it's gonna be if you wanted to like run the KVL on such a system. Okay, now the short part is use whatever you learned in the previous lesson. You have a parallel resistor R2 and R3. Okay, you simply can replace it by a equivalent resistance, right? And if you do that, now you have a simple circuit, one loop simple circuit. Okay, R1 and R equivalent. Now, either you could do a KVL, find the current and determine the voltage across the R1 and R equivalent, or you can simply do the voltage division, okay, and see what is the voltage across R equivalent and R1. Are we good? Now, if you calculate the R1, then you have the answer for the voltage across R1. What about the R2 and R3? Because right now, in the simplified version, you calculate the voltage across R equivalent. Well, R equivalent is the parallel connection of the 2 and 3. So if we have parallel resistance, we know that the shear voltage, what they add up in respect to the current. Are you okay? So whatever voltage is across the R equivalent is going to be the voltage across the R2 and R2. Very simple, very clear. Now in the lab, you want to like measure that is much simpler than that. You have the voltage source, you set the voltages, you connect the resistance, and you have the multimeter to measure the voltage across each resistance. Which by now you should know how to use that multimeter to measure the voltage. Measuring voltage, the multimeter is going to connect it in parallel with the component. So one probe to one terminal, another probe to another terminal. So this is going to be our voltmeter. Okay. The basic mistakes that you might have, or like the over kind of like looking some aspect, is that first connecting to the wrong, or connecting the probes to the wrong socket on the multimeter. This is very simple. Another part is to have an inaccurate range in your multimeter. So you want to measure millivolt, volt, okay? What type of range you have to set that. Next one, the voltage DC and AC in the digital multimeter have different settings. Actually, they have different, you have to turn the knob on different spots. So another thing that you need to pay attention to when you want to measure is to have the setting on the right type of both AC and DC. Are we good? Now, when you want to like calculate the voltage have a direction. In previous lab, you would measure the, sorry, not calculate, measure. You would measure the resistance. Resistance doesn't have direction. It's just called one number. But voltage has a direction, it's a vector. So how you connect the two probe, the common probe and the measurement probe on like each polarity, okay, is important. Not gonna change the number, but if you mess up that polarity, you are gonna see a minus sign on your the screen of the multimeter. Okay, not gonna change the value, but it's a wrong connection of the polarity. So try to practice, because later on in a complex network, it might create some problems. Okay, so very easy. You connect the two probes across resistance and measure the voltage, and you know how to calculate the errors and uncertainties and all these. You already done. Network B is a little bit challenging, and it's not like actually like a hard challenge. It's a very little, but you need to pay attention. We don't have current source in our lab. The sources that we have are all DC sources. Now, anyone can tell me how we can replicate this current source in our network using that voltage source?
Source transformation.
Go to a little bit more detail.
Well, you can kind of transform the current source that's in parallel with R1 into a voltage source in series with R1.
Then you're changing the network.
Yes.
The concept is true, okay? But if you change this, then you are not able to calculate the voltage across the R1.
Okay.
You know what I'm saying? Or measure the voltage across, because you change the R1 position.
Can we find an REQ and then what the voltage across the current source would be and supply agreement? So
Exactly. What the Thevenin told us? The Thevenin law told us that current, you can deal with the whole system as a black box. What type of voltage I have to like apply to the whole system to get the current I want? It is the Ohm law, voltage divided by the equivalent resistance of the system would give you the voltage you need in the source. Okay, so you would inject the current that you want to inject. This is theoretical part. The lab part is easier. What you do, you set your circuit, you connect the voltage source instead of the current source, okay? And you connect an ammeter before you start measurement. You connect the ammeter in series with your source. And this is going to be a voltage source. So you don't have this. This is going to be a voltage source. Okay? And then you start increasing the voltage until your ammeter shows the amount of current that the assignment asks you to have. Okay? Now you are having a voltage source that is actually replicating the current source you want. Is that clear? Now that you have that and you set your voltage source, you can eliminate that ammeter because you only have one digital multimeter. You need that. Okay? You eliminate that ammeter. You run the circuit with that estimated voltage source, with that voltage source that you find out, the amount of voltage that you find out, and you start measuring the voltage across each of those resistors. Is that clear? Now, theoretically, how to calculate the voltages is still the same as before. You have two series resistor, okay? You know how to calculate the R equivalent. Now you have two parallel resistor, R1 and R equivalent. You know how to run a KCL. What would be the current division between them? Okay? And if you have the current of each of them, okay? If you have the current of R1, easily you can calculate the voltage across R1. Are we good? And if you have the current going through the R2 and R3, since they are in series, they share the current. So again, using the Ohm law, you can calculate the voltage across these two resistors. Are we good? Any question? No? Now, this one is the interesting. You have a complex network, and the assignment asks you to represent the E1. Come on. E2 and E3 in a matrix form with the sources. Now you can name this one V1, this one V2. So yeah. Whenever I have Zoom, I have problem with my computer. Okay. The question asks you, the lab assignment asks you to represent the system and the voltage in a matrix form. Okay. So you can input the voltage 1 and voltage 2, and using the matrix, calculate what is going to be E1, E2, and E3. Are we good? This is the objective of this exercise. Now, look at the circuit. I'm going to give you a hint, but I'm going to let you to do the calculation. I hope you had the algebra, so you know how to work with matrix. Okay? And I think I already have a hint on the lab assignment. If no, there is a blue line hint, isn't? No, I will check that. I think maybe I uploaded the wrong file. Okay, so I'm gonna give you that thing. E1, look at this. This is ground. E1 is the voltage across that first voltage source that we have. Correct? So it won't change, and the circuit would not affect that. It's always going to be constant and equal to first voltage source. Are we good? So when you want to like calculate or like develop this matrix for, you can ignore E1 because it's not changing. It's not a variable. And you would estimate E2 and E3 based on V1 and V2. Come on. What is it? It is not working. So oh, it's closed. Come on. Well, Zoom is gonna get a very through email. Okay, I'm gonna just I want to like record that. It's not good. Okay, if you wanted to like represent the system, as we said, E1 is gonna be always constant, so it's not a variable. So you can represent the whole system as E2 and E3. A is the matrix that represents the system, and V1, V2. Now, how to calculate or how to estimate this matrix A? You have two options. Again, hard one and easy one. Yeah, go on. Oh, you don't have that. Sorry. Come on. Come on. Okay. So you have two options. Hard one, easy one. Hard one is to run a KVL. You have for loop to run a KVL and find out what is the relation between E2 and those sources. Okay. The easy one is to do KCL because we only have two nodes that are variable. And what is the KCL? The summation of all the currents should be equal to 0. Now you have one current here in E2, one here, and one here. What is the first current? Is E2 minus that V2 over R1. Correct? So it's going to be E2 minus V2 over R1. And you can do the rest of the currents. This is going to be E2 minus V1. This is V1 over R2. This is E2 minus E3 over R4. And this is E2 over R3. Correct? So you have one equation. You do the same for E3. So E3 minus V1 over R5, E3 over R6, and E3 minus E2 over R4. Now you have the second KCL. The summation of those currents should be 0. Okay? Now, you can separate all the terms that have E1, E2, and E3. So separate the terms for E2 and E3. And you can factorize those two out of those terms. So what you are going to end up is that you have, for the first example, for the first equation, you have E2 times a bunch of resistor, summation of a bunch of resistor. Correct? Plus E3 times summation of something. Minus V1 with the coefficients minus V2 with the coefficients equal to 0. Are we good? Now, same goes for the second equation. Now you can bring it to the matrix form, E1 and E2. So, sorry, E3 and E2. Now, what is getting multiplied by these two factors? For the first equation, this is going to be the first number that is multiplied by E2. So it's going to be the first parameters in your matrix. Now, this one is whatever you multiply to the E3 in the first equation. Are we good? All of that is equal. Now we bring the V1 and V2 on the other side. Now you have another matrix that is going to be multiplied by V1 and V2. Are we good? Any questions so far? Now, if you move this one to the other side, you have the end result. How to move that? You need to multiply both sides by that matrix inverse. Are we good? Then you have your system. Then whatever input is, V1 and V2, using that end matrix, you can find the V1 and V2, you can find the E2 and E3. And as we said, E1 is always constant. Is that clear? Are we good? Perfect. In lab, you could do two things in order to calculate the E1 and E2. One is you have two voltage source. You set the network, you connect the two voltage source, so your voltage supply has like 3 channel or at least 2 channel. Okay, so you have the ability to have 2 sources in your system. You simply set those 2 sources with the values, and you measure the voltage of E2 and E3 and E1, which is the one of the sources basically, as we said, and you have the result, and you can kind of like evaluate if that measurement is consistent with your calculation. Are we good? Now, what is the next one? Use the superposition. Do one source at a time. Measure the E2, E3, and E1. And then the end result is going to be the summation of the 2 measurements for each node. Is that clear? Are we good? Which I believe I asked the superposition in the assignment. Check that. I think I asked for the superposition one. So it's not an option, actually. You have to do that. Okay. Yeah. For the power consumption, again, is very easy. For calculation, you need to find, we want to like see what is the power consumption of this 15. You need to find what is the current going through that and what is the voltage across that. Then you have the power. Power is VI. Another approach is to simply just calculate the voltage, and the power is going to be V squared over R. You have the R, you calculate the voltage across that R, and you have the power. Are you good? How we can find the power? You have 2 series resistor that you can calculate the equivalent of that, let's say equivalent 1. Then you have 2 parallel that gives you the R equivalent 2. Now you have a voltage division that you can calculate the voltage across R equivalent 2. And since it's parallel of the 15 ohm or whatever is R equivalent 1, the voltage are the same. So whatever voltage is R equivalent 2 is the same as the voltage of the 15 ohm. You have that, you calculate the power. Are you good? Now, in lab, again, you construct your circuit, you apply the voltage at the source, okay? You have 2 measurements to make. One is to measure the voltage across this resistance, and another one is the current that goes through the resistance. Now, again, remember, voltage, the voltmeter connects in parallel with the component that we want to measure the voltage across it. The ammeter connects in series. Now, your digital multimeter has two probes, 2 sockets for ammeter. Connect to the proper range. They are 2 different range. Also, it has 2 options for ammeter based on the range. So if you put, like, for example, in milliamp, okay, the setting is milliamp, it is going to be accurate to measure the same range of the current. Okay? Another thing that you can miss. The default of the multimeter, when you put it in an ammeter, is AC. So if you just put the ammeter connected to that, and even if the range is correct, it's going to measure the incorrect value. You need to change the AC to DC so you can calculate the proper current. Are we good? So these are the important fact that you need to pay attention to. Now, we already talked about how to measure the voltage Thevenin-Norton current and the resistance. Now, we are going to go over that very fastly. This is the circuit that you have in your last assignment. Okay, the last exercise, exercise 4. And you wanted to find out what's happening between these two terminals. This is our load. We wanted to treat the rest of the circuit as black box. So create a Thevenin circuit and Norton circuit, the equivalent for these complex circuit. Again, you wanted to first of all, you might see those capacitors in the circuit and you say, okay, what's going on? We only talked about the resistance so far. Now, anyone can tell me why having those capacitors would not change anything for you guys? What would be the impedance of the capacitor in the DC? Open circuit. The impedance is 1 over J omega C, right? Omega is 0, so the impedance is infinity, so it's open circuit. Correct? So these are open circuits. So when you talk about the DC, it doesn't matter if they are there or not, it won't affect anything. Okay, so you can put it or eliminate it, it won't change it. Okay, now you wanted to calculate the Thevenin-Norton resistance. You deactivate the sources. Both of the sources are voltage source, so you short circuit them. And if you short circuit them, you have two parallel resistance. The resistance that we have here is different from the assignment. Okay, so don't look at this 5.1 kilo ohm. It's, I think, 12 kilo ohm. Okay, so you have two parallel one, all in series with another. Okay, you can calculate the resistance. Now you want a voltage across this two-way. One is to apply both voltage source, run the KVLs, and find out what is the voltage here when it is open source. Okay, so you don't have anything connected here. It's open circuit. Okay, so you can calculate the voltage here. So since it's open circuit, that means there is no current here. That means there is no voltage drop here. So the voltage in this terminal and voltage here is going to be equal to each other. So if you find the voltage here, you find the voltage at the terminal. This one is 0. Okay, so you find the voltage here, you find the voltage at terminal. Are we good? Very easy. Now another way is superposition, as we said. Okay, one source at a time, and then the total answer is going to be the summation of whatever you calculate for each of the sources. Same goes for the measurements. Okay, when you want to measure the V of Thevenin, you open a circuit, the load, apply the sources, and measure the voltage across that terminal. Okay, if you wanted to measure the current, you short circuit the terminal and measure the current going through that short circuit. No, you don't need a wire to short circuit, simply by connecting the ammeter to the two terminals. So you put the ammeter here, one terminal here, one terminal here. It already works as a short circuit. We good? So easily you can measure the amp of a short circuit. Is that clear? Now, I put an optional approach, again in superposition, to calculate all those values based on one source at a time. okay, and do that. There is a simulation also for exercise 4 in multisim. This is your first multisim simulation, okay? The manual of the multisim is over there, but I am gonna post a video of how you can safely create a schematic in the multisim. What are the components, where the component can be found, where the cross can be found, okay, and how you can run the simulation. Any question? Sorry? The license is on campus. I posted at the beginning. The preparation module, where I put the installation guide for the multisim. There is a text right. No. When you download, first of all, be careful to download the figure. Okay, so in the last version of the multisim, do not click on the big bottom that says download. Okay, there is a try for free, very little try for free. Okay, at the bottom of that bar. Okay, so click on that, download the free version. Then you want to activate for license. Okay, there is 3 options. Is the second. Okay, for activation, you have 3 options. Choose the second option and put the code that I put in the campus. Okay, and then it's going to be activated for the tool. If you have any problem, let me know. Okay, we have enough time because we are extending the lab for 2 weeks. Okay, we have enough time to deal with that. Okay, so if you have any problem with multisim, let me know. Thank you.